it is basically a sigmoid function of eta. Now, you may say sigmoid function, what is that? Well, if for those who have taken any other course in machine learning, immediately you say, wow, that's interesting, okay? So it comes, for now, what we're interested is we can reverse this and write mu as a unique function of eta, which in this case comes to be the logistic sigmoid function. Can you do this with other distributions? Let's see. Can you do this with a multinomial distribution? So it's like the Bernoulli, but now we have mu states, and each of them can happen with probability mu k. So yes, you can actually from there, you can write exponential of the sum, and there is the parameter theta, and it comes out that there eta k is log of mu k. But there is a problem here. When you write this distribution, that function a is not there, 0, okay? And later on, we will see that if that function is 0, we have a problem because this will predict that the moments will be 0 of the distribution. So just accept the fact that this alpha is 0 is not good news. Well, and in reality, this is not 0 because this derivation is wrong. And can you tell me what exactly? Well, it says there on the bottom. All right? What is wrong is that these parameters mu, from mu1 to mu m, they're not independent. They have to satisfy this, the sum has to be equal to 1. So what you need to do is, in this expansion, you have to get rid of the last term, mu subscript capital M, and you write this in terms of summation from k1 to m minus 1. And when you do that, with some trivial algebra, it comes up that nk from 1 to mu minus 1 is given by ln of mu k over mu capital M, where you have defined this mu of capital M to be 1 minus the summation from k to m minus 1 of the of mu k. So multinull distribution, of course, then it's an exponential family distribution, and you can compute the moments in terms of the natural parameter theta, and there is the calculation with some simple algebra that you see on the slide that I advise you to look, and it comes out a beautiful function, exponential of eta k divided by 1 plus the summation of these exponentials. And what function is that? My friends from computer science, do they recognize this function? What is that? Softmax. Okay? So you know that these functions don't come when you see them in the concept of logistic regression and all these things, don't come from nowhere. They're basically some mathematical reasoning with why they are the way they are. So this is the softmax function, and it's called softmax, and actually we will see this in plots as we go along. It looks like a soft version of the maximum function. So in any event, we can fit the distribution exactly to our exponential family distributions, okay? And this alpha is not anymore 0, but is log of the summation of these exponentials. And later on, we will see that, imagine here you have a log of the summation of the exponentials, okay? And this will give us headaches later on numerically, because this is not an easy term to compute, all right? But these functions are never easy to compute, okay? Because even in a physical context, in the physical world, you have significance that is very complicated. But here we have a log of the summation of the exponentials, okay? So we will need to deal with these things one way or another, okay? I think I may need this if I have time for my example. For the beta distribution, you can also write it as an exponential family distribution. So the natural parameters, you may want to remember, because I may use this on the fly, that there are a minus 1 and b minus 1. So a and b come in the moment parameterization. Eta comes to be, you know, there's no algebra really, it's just looking at it. And then this function alpha comes to be the log of the gamma function A gamma of B divided by gamma A plus B. Okay. You may ask, where is Gaussian? Come on, Gaussian, of course, exponential family, right? Come on. There is really nothing to fancy about the Gaussian. We already have done it because we discussed about the canonical form of the Gaussian. Let me prove another item from your homework. All right? Has anybody shown this already? Have you looked at this, or you were waiting for your TA to come? Because he told me after I discussed this in lecture, he's not going to do this. Okay? So, how about this amazing result? And you tell me if you like it. If you want to calculate the expectation of the sufficient statistic, it comes to be equal to the gradient of that function A with respect to eta. This is not an approximation, this is an exact answer, an exact result. The expectation of U of the sufficient statistics, it comes out to be the gradient of A with respect to eta. Anybody who already proved it? All right, our TA, he proved this when he was flying back. He said, to keep my brain alert, I'm going to do this calculation, okay? While at the same time drinking the last beer coming from Ireland, I suppose. Okay, so here's the calculation, and see how simple it is, right? This is our distribution in the general form. So what I'm going to do is, I am going to take, if I normalize this, if I integrate in x, I get equal to 1, because this is a normalized distribution. So consider an integral of this equation, the second equation, integrate it in x, equal to 1, and take derivatives with respect to eta. Take derivatives with respect to eta. So there is an eta there, so gradient of g times the integral of the rest. And then there is g of eta, all right? And then you're going to have the derivative of this with respect to eta. You're going to get a u outside the exponential. We agree? All right. So do the following. Multiply here by g and divide by g. What is g times this integral? What is g times this integral? This integral times g, how much is that? 1. So if you put this term on the other hand side, on the right hand side, you're going to get minus gradient of g over g equal g of eta times and this term. And what is that? What is g of eta times a times that? That's our distribution. And then I have integral with this distribution of u. What is that? By definition, is the expectation of u. So it comes out that the expectation of u is exactly the gradient of a with respect to eta. Now, I mean, it's a coincidence. You will say, well, you know what? This includes many, many, many distributions. So basically, it's an extremely desirable result, okay? And can you push this further? Yeah. You know what? If you take the second derivative of a with respect to eta, it comes to be the covariance of u of x, of the sufficient statistics. And if you want to go to higher order moments, you can keep going. But there is an important result here, okay? Do you agree that the covariance of u is, positive, non-negative, it's positive semi-definite, basically, all right? So what does it imply for the function a of eta? What type of function then a of eta comes to be? It comes to be convex. And if the function is convex, you know what that means? Look at this equation. You don't have to read everything. We just proved basically the function is convex, okay? And effectively that means if you look at this equation, right, the moment equal to the expectation of u is equal to the gradient of a. Because a is convex, means this equation of mu equal to gradient of a, it's invertible. So for all of these distributions, you can write uniquely eta in terms of mu, the same way you can write mu in terms of eta. So there is no ambiguity, there's no like